Shaders programming in OpenGL. What is OpenGL pipeline? Means how we draw OpenGL graphics. I mean, OpenGL is a game of vertices. I specify vertices. Then I say these vertices belongs to triangle. This vertices belongs to quad. These vertices belongs to lines. And I provide vertices attributes like normal for the lighting, texture, other attributes. And then I get it done. So, I mean, what's happening kind of behind the scene? Like I am setting vertices primitive, normal, vertex coordinates, it's normal for the lighting and coloring or texture coordinates. And then it's done. So, OpenGL pipelining is from setting vertices to finally seeing the output in the video world. So, how OpenGL works? Like if I set vertices, then after setting the vertices, we set vertices attributes. Okay. Once vertices attribute is set, then means from my part, I think we are done. Means vertices belongs to which primitive and vertices attribute. What extra we do is transformation, like geometry, we rotate, translate. So if we rotate and translate, if we do the geometry, we start from vertices. We do the transformation. Now vertices get transformed. Once we are done with the transformation, then I have new vertices. Old vertices gone, because after the transformation, the vertices change. Once vertices change, then along with all the vertices, anyway I have the attributes. So once I have the attributes set, now I have new vertices. So with the new set of vertices, an attribute set, and we know the primitive, then OpenGL tries to get its edges, vertices with primitives. Now transformation story is over. Means OpenGL has got new set of vertices. What I had said, I did some transformation. OpenGL received new set of vertices after some computation. So new set of vertices with its primitive. Then OpenGL tries to set the with the new vertices with the primitive. OpenGL tries to get its surface. I know what it is. I know its primitive. It is a triangle. This area is triangle. This area is quad. This area is line. Then I can draw edges. And after that, I can estimate the surfaces. That procedure is called rasterization. Vertices, primitives to the surfaces. It is called rasterization. So once surfaces are determined, means now I have complete surface coordinates. I have pixels. So input was vertices. Now I have pixels. So vertices, transformation, new set of vertices with primitive. After rasterization, I am getting all the surface pixels. What is remaining now? Since vertices has lighting, so lighting will be done. Now, since vertices has a normal, then lighting will be done. Since vertices have textures, or if it has colors, then pixel will start getting colors. Means texture is nothing but colors only. Once texturing is done, and if a different property is set for the lighting module for the specular, then again lighting computation would happen. There is another uh, uh, other models in the lighting. So those models will be taken care. And finally, the new set of pixel coloring. So pixel coloring, lighting, texturing, lighting, and at the end, it generates the pixel colors. This procedure is called fragmentation. Vertex transformation, rasterization, and then coloring. Coloring is called fragmentation. One fragmentation is done, then again with the kind of previous surface blending may happen. Then depth cutting will happen. Whatever, if depth is enabled, whatever pixels that should not be shown that go behind should be cut out. And then stencil and those operations, and then finally whatever comes in that will go to the color frame buffer and video frame. What we see here, can we see something? Means from setting vertex coordinates, vertex attributes, to getting the final color frame buffer. So, means what is the kind of something different are we getting? There are two areas which are mathematically computational rich. There are too much computation happening. One is geometry, transformation. Transformation is nothing but matrix multiplication. How much matrix multiplication is costly at CPU usage, anyone can try. You can try multiplying two matrices and order of 3, order of 4, order of 5. You can see how much CPU takes the time. So, if I go for transformation, transformation is nothing but matrices, and then keep going transformation, then finally it will lead to so many matrix multiplication. So, vertices transform into new vertices. That is transformation. So that is computation rich. Then once we do the rasterization, after that coloring, light computation, texture computation, then light computation, that is highly CPU kind of intensive. So geometry and geometry 2. In geometry, we can then think of tessellation also. So tessellation also needs a high computation. Can we push this transformation operation and fragmentation operation to somewhere which is highest speed computation? So that is a shaders program. So there is a new hardware unit comes into the picture. That is called GPU, Graphics Processing Unit. And GPU is highly advanced in matrix multiplication. So what we can do is, once we receive vertex and vertex attributes, we can just push into the GPU memory, GPU buffer, and then we can give a hint that these are the computations that you have to do. And once it is done, then I receive the final vertex. So that area, so how we can push in the data to the GPU and how I can guide GPU. So GPU should be programmable, means we can program the GPU to do something. So GPU is not a kind of any decision-making entity in OpenGL. It's a kind of helper. So in image pipelining, we use GPU in between to do something and then get back the result, so that it will be quick. So if I am asking GPU to do what is transformation, then GPU should be programmable. In what language it should be programmable? That is called shaders language. Okay. So GLSL, graphics shaders language. So there are compilers. So GPU, so we write in the shader, it's a kind of C, main, and curly braces and semicolon at the end of the line. Okay, types. So like if we have int type and like that, there also types are there. So what we do is we write code in the shaders language, compile it through compiler. Now in shaders language we place hooks to receive the input, and there are hooks. From there we can get the output. Means we can get our work done through through GPU. So for the vertices, what is vertex transform for vertex computation? So we have one shader called vertex shader. So we write vertex shader, and there we place hooks for input like our what is it? Means if I see the traditional fixed function pipelining, then what we do? We have an array, like I have a big array. In array I have vertices, and I have color, I have normal, I have texture, everything kind of mixed in one array. Okay, and that array, while drawing it like GL draw element or GL draw array, so we just specify indexes here and there in the array, and our work is done in one go. That full array, that is called vertex array, we push inside the GPU with vertices, with normal, with color, with texture, and indices and everything go inside. So we keep it like here we had an array on this side. There it is called vertex array also. And inside the array we have attributes, that is called VB, vertex buffer. So set of VBO inside VO. Here set of attribute data inside a big array. Same. So what we do is we copy our full array into the buffer inside the GPU. Okay, and then we write our vertex shader, and in vertex shader we write the mathematics. I want projection matrix to be multiplied with view matrix to be multiplied with model. Okay, model matrix then multiplied by our model. Okay, and so we can write there whatever we want to be multiplied, that data we can push. So vertex shader is nothing but like vertices transformed into new vertices. Now new vertices would be passed to another shader. Means since we see the computation rich in two areas, fragmentation. Once we have new vertices, we know the primitives, and we have vertex attributes, then again OpenGL will do the fragmentation, the coloring of each pixel. So that's what we'll see, that how we can use the GPU first of all, where GPU fits in our OpenGL pipelining, the two places GPU fits in, how we can push data inside the GPU, take out the data, push inside the GPU again for the fragmentation, take out the color from the whatever is kind of computed and display it. Okay, so in OpenGL pipelining, what we have been doing in the fixed function pipelining, everything was done by CPU. Now geometry, vertex computation and fragment computation we will use with the computation we will do in GPU, and how we use GPU through shaders programming, that we'll see. Further to our discussion, we'll proceed on this too. So this is Linux Mint. Point by point. Okay, so discussion is about shaders programming in OpenGL. So OpenGL works with OpenGL pipelining. There is a pipeline in OpenGL. Okay, and vertex operation and fragmentation were delegated to GPU. So there is a new entity called GPU. Otherwise, everything happens on CPU. So now there is something called GPU. So graphics processing unit does fast mathematical computation. The way we discussed that there are few matrix multiplications, manipulations those are kind of computation rich and costly. So and time consuming. So that is kind of delegated to GPU. We are using an example 3.1.5 PY OpenGL package, which has GLSL 1.4. Okay, what is the simplest kind of OpenGL pipeline? There is application. There is a geometry. One geometry is finalized and there is a rasterization and there is that's it. So this is what we are talking. So application, geometry, rasterizer, image. Geometry area would go to vertex shader and rasterizer area more or less it would go to fragmentation shader, fragment shader. So this is typical OpenGL pipeline, kind of what we saw. And like first we have vertex normal color. So this is the vertex shader where we do all the transformation. Then we come to a kind of a shape with transformed vertices and then along with primitives. So this is kind of a shape that is drawn. And now rasterization happens and it is turned into pixels. Once it is turned into pixels, then it goes to fragment shader. Fragment processing, texturing, lighting, everything happened per fragment basis. And pixels get color. Then blending, depth, cutting and stencil, those tests happen here. And then it goes to video framework. Okay. So pretty simple. Means we start with the vertex, normal, color, whatever we specify. It goes with various transformations and then we get new vertices. If we add the primitive, we get shape like this. And with rasterization, after rasterization, we get the pixel surface and surface pixels. Then after fragmentation, we get coloring of the pixel. And then we do kind of various blending operation or test, depth test, stencil test. And net pixel with color goes to framework. So that is the pipelining. Okay, what is CPU? Generally, CPU has control unit, ALU, arithmetic logic unit, and cache and RAM, whereas GPU has RAM and only ALU, means because it does mathematical computation. So it has kind of high speed set of ALU, and it has cache where we can push in the data. Okay, in CPU what we has vertex array, color array, normal array, texel array, and then we use a call like GLDraw arrays, GLDraw element, which kind of index into these array and draw the what we want. But in GPU, we have vertex array object, means full whatever we see, everything goes in vertex array object, and one vertex array object has many VBOs. Each entry is one VBO. Vertex array, vertex buffer object, vertex array object. Vertex array object has everything. Buffer object 1 means vertex, color, normal, texture. Okay. So these are cache in GPU. The cache what we are seeing. So in this cache, we store a full vertex array. It's a vertex, color, normal, all the attributes. And then we call GL draw element. Okay. Then we call GL draw element. Okay. So that is the scenario. Now everything is, since if we are working on GPU and we are using GPU at these stages, like one at this transformation and one at vertex fragmentation. So there at two places we are using GPU. GPU cache, we have to copy all this data in this format, and then we say GL draw array or GL draw. Okay, so GPU runs code, means compiled code, and this is typical vertex array, vertex shader code, and this is fragment shader code. So here we receive a uniform data. There is a uniform data, means data which will not change all along. Once we push in, like model view matrix or projection matrix, once we push in through the program, then it will not change. And attributes which would change, like here it is changing, like IN color or any computation we can use. Varying, which would from vertex shader to fragment shader we can pass in. So the positions goes into kind of built-in variable GL position, where color we are copying and passing here. So we are making a fix, whatever color we are receiving, just we are converting it to vector of 4 and then assigning into GL frag color. So this is the kind of simple vertex shader and fragment shader. So vertex shader code we push from the main program. Okay, so from application we push the data into the vertex shader, and then after rasterization, then fragment shader executes per fragment. Vertex shader execute per vertex. Fragment shader execute per fragment. Fragment is a kind of a set of pixel which has a common color, or we can consider as a pixel. So per pixel operation, a coloring happens here. So here we copy all the data here, and then we call the vertex shader. These attributes we pass from the program. Whatever we write the program, these attributes we pass in the shader, and it does the we rely upon the computation. These computation we rely upon it, and then we return the rotated position, and that position finally goes to rasterization process, and rasterized pixels per pixel operation will come here, and we generate the fragment color. So that is the scenario. Okay, so in lab session we will have pyramid. So that is the idea generated. So what we would do is we will first develop our code in CPU mode, and then we will translate it to GPU, so that we will understand that how we call CPU and GPU. Okay, so we will start. We will create directory GLSL. Okay, so we will have a file called fgl.py, GLCPU.py. So this is for CPU. So this is a traditional code we'll write. So probably what we can do is, from OpenGL.glu, GL import everything from OpenGL.glu, import everything from OpenGL.gl, import everything. Okay, so that is the concept, and then we will have a init function, def init, and GL clear color. Now we have kind of so GL enable client state, GL color array, GL enable client state, GL vertex array, GL color point, 3 GL float 0, and color array we will write. So we have kind of the way we showed in the example. Okay, so 1 2 3 1 2 3 4 5, we have 1 2 3 4 5, we have 5 vertices. For that we will write the color, kind of 1 0 0 is red. Okay, I think it would be nice if we write the vertex first, GL vertex pointer, and here we will have 3, that is stride is 3, GL data is GL float type starting from 0, and what it is data. So I shall say kind of minus 0.6 0 0 0.6 0 0 0 0.9 0, okay, 0 0 1 0 0 minus 1. I think it is understandable what it is. So left side, right side, top, okay, far and 1 is behind. So this is 5 vertices of a pyramid. Now color pointer we will kind of set 1 0 0, and then 1 0 0, then 1 1 0, then 0 0 1, then 0 0. So this is the color we have kind of set for. So this is the code till now. So GL vertex pointer, we have set the vertices 0 9, I think it's perfect, and color we have set. Okay, so we are done. Now we'll set GL shade model, GL smooth, and GL enable, GL depth test. Okay, so we are finished with the test. Okay, so we'll write the display, def display, GL clear, GL color, buffer width, GL depth, buffer width, GL push matrix, GL translate -4. Okay, GL draw element, GL draw elements, GL triangles 3. I was trying GL multi draw element, but somehow it is not coming. GL unsigned byte 0, 1, 2. Okay, so we'll just copy paste this few times till we resolve GL multi draw element. Okay, so GL triangles 3, GL unsigned byte 0. So these are the vertices. Now we'll replace this with 1, 3, 2. Okay, so idea is these are indices 0, 1, 2 means first vertices, 0 vertices 1 and 2. 1 and okay, this one. Now 1, 3, 2 means this, 1, 3, 2 will be this, and then 3 is this, and then 2. So like this we are drawing GL triangles. So we'll substitute this with 3, 2, 0, 0, 1, 3, 0, 4, 2, 1, 2, 4, 0, 4, 2. Okay, so 0, 4, 2, 1, 2, 4, 0. Okay, so we don't need 0, 4, 2 again. So 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2 is 1. 1, 3, 2, 3, 2, 0, 1, 0, 1, 3. 0, 0, 4, 2 on one surface. 1, 2, 4 another surface. And 0, 4, 1. So I believe it will be 1. Okay, so 0, 0, 4, 2, one surface, and 1, 2, 4, one surface, and bottom is 0, 4, 1. And here the bottom is 0, 1, 3. Okay, so pretty well. And this is 1, 0, 1, 2, one surface, 0, 1, 1, 3, 2, one surface, and 3, 2, 0. I believe it's all right. 0, 1, 2, 1, 3, 2, 3, 2, 0. So perfect. Now we'll say GL pop matrix. We'll use double buffer. So I'll say glut swap buffers. Now def reshape. Okay, so I think it's advisable that we can copy this code from the last written. So we had quadrics. So in quadric we already have this code, so we'll just copy paste. Okay, so we have init, we have display, and then we have reshape. Okay, and 0.5 to 10, and here we'll use double, and here the example is GLSL. That's it. There is no keyboard we don't want right now. Okay, so glut init, init display mode, glut init window size, glut in the window position, create window init, display func, reshape func, glut. And in reshape we have matrix mode projection, load identity, perspective, model view, load identity. So when it comes to display, then we translate it to -4, so it go in the middle, and then we'll draw and we'll pop. So while drawing, we already have data in the already set, client state color and vertex array, and then we can disable it once we are done. So I think just we leave it, and then GL vertex pointer and color pointer and smooth, and so I think we can try Python. Oh, it came. Okay, so this is a pyramid. Okay, how this is a pyramid I can't prove, slowly we'll prove. Okay, so we'll prove slowly. Okay, so I have a library called OpenGL utility that has a keyboard function. So we'll copy this here. So we'll copy this code. Now we have two files. OpenGL utility has def keyboard, and pressing few key it does some, it returns a transformation, kind of what we do the transformation, like we are doing transformation like GL translate. So whatever with the key transformation we are doing, that it would return. So I'll say kind of from OpenGL util import util C util I equal to util C, and here we'll have a transformation equal to empty, and here we'll set the transformation. So we'll have a kind of a keyboard function, def keyboard key x and y. Okay, key equal to byte, so make sure it is a byte. And now we will call util I keyboard, whatever we have imported now, and pass the key, and we expect the modified transformation. I mean, we can print it if we want. Like if I say key equal to if I say verbose, then it would print at the transformation method. Okay, so glut post re display. So now we have keyboard, and if I press something, then transformation matrix would change. And now this transformation matrix kind of will use its magic here. Okay, so we'll write what we want. So we'll say this is Python translate if len of x equal to 3 GLSL rotate for x in transformation. Okay, so we kind of iterate transformation and we do translation and rotation based upon its length. So for rotation, length is 3. For rotation, length is 4. And translation length is 3. That's it. So we'll try again. Python 3FGL. So we'll press a kind of keyboard like Y. It is rotating. X, Z. Okay, so I can rotate on the fixed axis also. So this is along x axis. So it is working. So this is a pyramid. This is pyramid. I can rotate along y axis. Okay. Okay. I mean, I can move it also. It is coming toward the camera. Or if it is in this direction, then I can move up. Okay. With a fixed axis, I can move right, left, up, down. Okay. Rotation is on y axis. Okay, so this is what we are doing. Okay, so what we are doing is I think it is rotated. I don't know what was the original. Okay, so this is what I wanted. Okay, so this is with the CPU, means code is written in the CPU. Now, few operations we will transfer it to GPU. So we'll write GPU code, and it will be big code because we will use shaders programming and so many things. Okay, so we'll modify this code now. Or I can just copy this FGL, PY, FGL. I can say GPU. Okay, so we are at code now will execute it for GPU. So what we need to add now? So we'll import numpy as np because we need float 32, and now we'll write the shader code. So I'll say word code equal to so this is the version we are using 1.40 and uniform mat4 matrix for UMB matrix, projection matrix, attribute. So attribute would change in the program, so it is vector 3 and in position. So this will come through VBU. Attribute vector 3. So this is color. Now we have varying, that is vector 3 and vertex color, wide main, vertex color equal to, or we can say vector 4 in color 1.0 and it is vector 4. So we are converting color to vector 4. Okay, and GL position equal to UP projection matrix multiplied by MB matrix, model view matrix multiplied by vector 4 1.0. Okay, so this is the code. Means vertex color we are exporting, it is varying. Now we will have fragment shader, frag code. This Python has everything. If you want kind of writing a file, version 140 and varying vec4 word color and wide main. So this is a C kind of code. So this will be called per fragment. Okay, so frag color equal to vec4. I think vec4 anyway, just we can say what color. Okay, that's it. Okay, so we have vertex shader code and we have P matrix color and varying word color. Word color is vector 4 version of this GL position. So we are doing matrix multiplication. And then frag code, varying word color, again main GL frag color is word. That's it. Okay, so we'll have a global parameter like shader program that we will use across V of vertex array object equal to none, and in it we will do everything now. So since we will change this, we will set it to global shader program VA option. Okay, we have set GL clear color. So I don't think we need this. Now we'll have we'll create shed. We'll read shader and we'll compile it. So that is the idea. So we'll say kind of word shader equal to GL create shader. I could have used some library, but I think for now it's okay. GL vertex shader, GL shader source, word shader, word. Okay, so word code. So vertex code what we have written. So for this vertex shader, we are setting this vertex code. Now we'll compile GL compile shader. Okay, that's it. Now same thing we'll do for kind of fragment shader, frag shader, fragment shader, and it is frag code, and here it is frag shader, frag. So we are kind of we vertex shader and both fragment shader we have compiled. Okay, now we will have kind of shader program equal to GL create program, GL attach shader, shader program, vert shader, GL attach shader, shader program, and frag shader. Okay, GL. Okay, now we expect a few things, so that we'll see. Now we'll just link it, GL link program, and we'll link shader program. So shader program is available now. So this shader program guy, it is available now for the processing. Okay, so error conditions we are not setting, expecting it should work in order to save the time. Now we'll create the VAO vertex object the way we described. So this one, VAO and VBO. So we'll say kind of a pos buffer equal to GL generate a buffer of size 1. Okay, GL bind buffer, so GL array buffer, pos buffer, GL buffer data, GL array, buffer np dot array, and here in this array we will set the array what we have set, CPU. So these two. So vertex we will set first. GPU. Okay, it was here only. Okay, so this is what we have to set. So np array, okay, and data type equal to np dot float 32. So this is np array, and it is a static draw. Okay, now we'll have a color buffer, so we'll do copy paste. Okay, so it is color. This is VBO we are generating. So color buffer and GL array. Now this array will change. Now this is this color. Okay, and it is float 32, GL static draw. Okay, so color buffer and buffer data. So these two VBO Now we have declared. Now we will have Mr. VAO, big boss. So VAO opt equal to GL gen vertex array of size 1, GL bind vertex array VA opt. We can see whatever we have done here in these 4 lines, this much we are doing. So we had these two as array. Now these two came here in this grammar. Now there is another guy called VA object, that is a kind of big wrapper, GL bind VA object. And now we'll kind of set it. So we'll have a GL enable vertex attrib array, okay, vertex attrib array. So now we have to enable these BBOs. So one is vertex BBO, one is color BBO. These in shader code, these would come as attribute in pos and in color. These will have index like 0 and 1, but we don't know. So what we can do is we have to set index here. Okay. So here in the index we can kind of by default it is 0 and 1. First one will be 0 and second one will be 1. So we'll set 0 and 1. But we have to find it out with called GL get attrib location. So with that, or we can just write it. There is no shame in that. So vertex location equal to GL get attrib location shader program in pos and color location is in color. Now I'll set this as vertex lock enable and color lock. Okay, so we are done. So this is little bit, means we can kind of place in some library and we can call a function to do this much. Now GL bind buffer, GL array buffer, pos buffer. Okay, now earlier we had these pointers which tell the grammar of this first array data and its grammar, what is the stride and where from we begin and what is the type. So that is replaced by GL vertex attrib pointer. Okay, so first is vertex lock and again it is 3, stride 3, GL float, same story. GL false, 0 and none. Okay, so this is for now same thing we'll do for color also. So GL bind buffer, color, call buffer, and here it will become color location. Okay, we can print it. Vertex lock, color lock. Okay, so it is color lock 3. Okay, no change. So now we have a pos buffer, GL bind buffer, pos buffer, GL bind buffer, color buffer, and here we are setting the color. Okay, so I think just these are available only for reference, so we can just comment it. Okay, there is nothing more in it. Okay, so now we'll move to display, and here we have the same story, push matrix. Okay, so what we have done now in the shader program. In the shader program, we have pushed the data, IN pos and IN color. Now we'll push data for matrices also, because these four things are there: color, these two guys, and IN pos. So two we have already pushed in this fashion, in this big kind of epic. Now we will push others. So we'll get like the way we got the attribute location, GL get attribute location, we'll get GL uniform location. Okay, so here only probably. Okay, so every time probably we can push in here only. Okay, where are these locations? So I can say UMB matrix equal to GL get uniform location, shader program UMB matrix, and here UP projection matrix uniform location P matrix. Okay, the way we did, I think we can print all together in one go. I mean, I can remove this, and here I can print these guys also. UMB matrix UP matrix Okay, now it is crystal clear. So now these two guys will go here because we'll use this later. Okay, so we'll set it as a global. So that is UMB matrix and equal to UP matrix. So we'll set in global here also, UMB matrix UP matrix. So whatever we are getting here, okay, so that will be remembered. Now we'll come to display to start to continue our story. Okay, so we have done this. Now we'll say GL use program shader program GL bind vertex array VO vertex array object GL uniform matrix 4. Now we are pushing. Here we pushed GL bind buffer and GL vertex attribute pointer. Here we push the data in pos buffer and call buffer. Okay, what is so what is pos buffer? Pos buffer is just a buffer. Okay, where we are pushing, one is pushing in vertex location, one is pushing in color location. Now we will push the uniform data. So GL uniform matrix 4 FV and UMB matrix 1 GL false GL get float V GL model view, whatever model view matrix we are receiving. So whatever the transformation we are doing, that is stored in model view matrix, that matrix we are fetching and we are setting. Now here it will be projection matrix and here it will be projection. Okay, so these two matrices we are setting, and now done. That's it. So we can draw, or we'll see first. Okay, so we have utility for the keyboard transformation. So this is the shader code. Okay, and this is fragment vertex shader and this is fragment shader. GL frag color, GL position. Now we are vertex shader code and frag shader code. Both we are setting into shader program, create a program, attaching it and linking it, compiling it. And now we have VBO, I should rather say it is a VBO1, something like that, and VBO2. Okay, so VBO is general buffer 1, pause buffer. Okay, so and then we push the data into the buffer. It is NP array and type is GL float 32, GL draw, VBO2, call buffer, and it is the data. Now we get the attribute location. What is the location in the fragment? So it would be a number 0, 1. Now it is VAO, and inside VAO, okay, now we have array vertex location and enable vertex array. So both vertex and color we are enabling the way we are doing here, enable client state. And then GL bind buffer, pause buffer, and then vertex location we are setting, and then bind buffer, call buffer. So both BBO, so this guy VAO contains VBO1 and VBO2. Okay, so this is VBO1 and this is VBO2. Okay, like that we are getting a uniform location of the MB matrix and P matrix, and we are storing in these variables, we are printing it, and in display we use the program bind VA object. So these I have not set as global because anyway it is read only, we are not writing to it, so it's okay. And now we are setting these to actual GL model view matrix and projection matrix, whatever we are receiving, and we are drawing. Okay, we can try our luck. Python 3F GPU. Gen buffer is not defined. FGL GPU line 48. Okay, so pause buffer is gen buffer. What is that? Gen buffers. Gen. Okay. Line 48. Buffers. Okay, so it is giving error. It is not able to find vertex location. GL get attribute location. Okay, so probably we will put some debug message. I think we skipped deliberately. We'll try now debugging it. So I can set here, if not GL get shader IV if not get GL get program IV shader program GL link status, then we can just say print error, and we'll say if prints it. So if not GL get program IV, okay, so let's see if we are able to do something. So Python GLFGL GPU, okay, oh, there is error, okay, there is some error, and later it is showing in GL get attribute location. Okay, error is not printed. What is the error? Okay, so there is some problem in shader code. Okay, so we'll try with kind of placing error here also. We skipped it, but I think we have to do now finally. If not GL shader GL get shader IV rag shader GL compile status. Okay, print what the error is. GL get shader info log rag shader Let's see if we can get something here. Error GL get shader info log rag shader. Okay, so GL flag color. Okay. GL flag color. Okay, now we'll try again. '66 array is array. Oh, okay, so we get it. Okay, so we'll kind of rotate. Okay, we can kind of move. So it is coming near us. I'm sorry. Moving to the camera. Going away from the camera. Okay, so we'll compare these two outputs. So I'll say Python GL FGL CPU. At least beginning should be same. So that is the concept, it is same. So this is CPU and this is GPU. Here I am doing across X 3 times, 1, 2, 3, and then I go Y 4 times, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. Both are exactly same. Okay. So this is what we wanted to achieve. Okay.